Hey everyone, this is Daniel for Rock the JVM, and this video will introduce you to Scala 3 macros. Now, this is a video that has been requested for a lot of time, and in this video, you're going to learn how Scala macros work and why they're useful. So here you'll have the opportunity to try out some of the most magical Scala code that you'll ever write. So the assumptions are that you are comfortable with Scala, obviously, and that you know what inlines are. We recently made a video on the Rock the JVM channel on how inlines work. Obviously, the best way to make use out of this video is to run this code and experiment yourself, and also refer to this video or to the article at the blog with the link in the description if you want to get back to these topics. Now, this topic is something that I talk about at length in my Scala macros and metaprogramming course. This is a long-form course on pretty much everything you need to know about metaprogramming, so the ability to create statically typed correct Scala code at compile time dynamically depending on what you need. So this course will get you all the skills you need to become a true Scala wizard and be able to write productivity tools for yourself or your team with macros and the most magical parts of the Scala language. We write several thousand lines of code in the course, and we also have 2 projects that will get you to appreciate both the magic of Scala and also the kind of work that tooling and library authors do for the community. So if you're interested, I'm going to leave a link in the description. These are skills that only a select few people have, like the Scala compiler team and a few others who learned on their own, like myself and other contributors and library authors in the Scala ecosystem. So I thought it would be great if more people have these skills, which is why I've made this course, and which is why I'm recording the video that you're watching right now. And speaking of which, let's go back to our own problems and let's discuss what macros are. So this is an SBT project that I've made from scratch. You can create a Scala empty project yourself. I only added a Scala compiler option to print whatever is inlined. So I added this compiler option -x print post inlining and also added the mask inlines to 100,000. This is really excessive, but it won't hurt for this particular project. So if you want to make an SBT project from scratch, these are the settings that I use. I also will leave a link to the GitHub repository of this video in the description. All right. So what are macros? Macros are a technique for metaprogramming. And metaprogramming means that you can manipulate a well-formed program and obtain another program which is in some way better. And so Scala macros are a way to manipulate Scala code and obtain other Scala code within the Scala language, which is kind of an inception way to look at it. But let me try to make a little bit more sense. So let's assume that we aren't dealing with a Scala language, but we're rather dealing with a very simple programming language, and I'm going to use the scientific calculator as an example. So let's say that you write text, which is in the syntax of a scientific calculator, like 2 plus 3 divided by 4 plus 2 times 8, or something like that. And that is a proper expression that you say that you send to the calculator to say compile and run, and that will give you the final result. Now, in order for the calculator to compute the sort of expression, it has to parse it out, and it has to figure out which operations need to execute first and which it has to execute later. So if we were to design a programming language that would represent expressions like this, we would define some sort of interface, and I'm going to use Scala code to do that. I'm going to have a trait expr, and I'm going to have some case classes for all the potential operations that we might want to support for calculator language. So for example, I would say a case class for sum that would take, let's have a case class for a number first. Let's say a number with a value which is a double, let's say. Let's say that the calculator works with doubles, and this extends expr. Then we have sum, which has 2 expressions, one on the left-hand side, which is an expr, and right-hand side, which is an expr. And this obviously extends expr. And we have a case class for sum, subtract, multiply, divide. Okay, so we have sum, subtract, multiply, and divide. And maybe we want to have case classes for other kinds of operations, like sine of 30. In this case, we would have a case class for sine with an expression, and this extends expr, and so on and so forth. Okay, so you get the idea. Now, in order for the calculator to evaluate this expression, it would have to parse it out into a data structure that resembles something like this. So for this particular expression, that would be something along the lines of a sum where the left-hand side is the number 2, and the right-hand side is another sum where you have the left-hand side, the division between 3 and 4, so div with number 3 and number 4. Then we have on the right-hand side the multiplication, so we have a multiplication where the left-hand side is a number 2, and the right-hand side is another multiplication where the left-hand side is number 8. So num8, and then we have sine with num30. Okay, so this data structure would resemble the kind of natural mathematical expression that I wrote here at the top. This, my friends, is called an abstract syntax tree, or an AST for short. And any programming language will have to resort to an AST to be able to describe what is possible in that language. So for a language like Scala, the class definition or a value definition or a method definition or mathematical expressions or method invocations or pretty much everything else that you can express in Scala can and will be represented by a node in an AST. And our goal as a macro programmer in Scala is to manipulate these ASTs into other ASTs that will then later be compiled to something that can be executed on the computer. So the way that a compiler works is that you have like the text language, so text compiled to an AST and then to a binary, obviously in a very, very high level. So every programming language will have some sort of interpreter that will semantically and syntactically analyze your code into a data structure that it can then evaluate or compile to a binary that will give the computer rules to evaluate a data structure like that. Obviously, modern programming languages have more than just 2 compiler phases. The Scala language has several dozen phases, but in general, the process looks something like this. Now, macros give us the ability to manipulate the AST before it turns into a binary. So if you want to expand this sort of process, you have text and then AST and then some sort of black magic that manipulates the AST into a better AST, and then that turns into a binary. And this, my friends, is where we step in. So macros are the ability to process ASTs that the Scala compiler successfully parsed at that point and turn that AST into another kind of AST that we can process as we see fit. And then that successful AST is then further down processed into the compiler pipeline into a binary. Now, the trouble is that once an AST has been built, we don't have access to the same source code, the same Scala code to be able to process that AST into another kind of AST, which is why macros or AST manipulation has been historically hard for compiled languages like Scala and Java and stuff like that. AST manipulation is very hard once you leave the host language, which is what happens once you obtain the AST, you lose the ability to interact with the host language. Up until Scala 3, which gives us the ability to process well-typed AST in the same language. So the way that macros work is that if you want to get into a backdoor to access the same language and process your AST, you can obtain an AST from a Scala expression, which is a piece of text, to obtain an AST via a process called quoting, and then manipulate that AST and obtain a new AST, and then reinsert that AST back into the compiler pipeline or via a process called splicing. So this process essentially lengthens the compiler pipeline, but gives us the ability to process well-typed AST at compile time. Let me give some examples of how that would work. In order for a macro to work, we need these 2 pieces, quoting and splicing. Quoting is the ability to take a Scala expression and turn that into one of these expert data structures that we can manipulate with the same language. Now, once we're ready to reinsert that AST back into the compiler pipeline, that action is called splicing. So let me demonstrate an easy example of a macro. So all macros are inline methods. So you know by now that inlines simply copy the method implementation at the call site. So let's have an inline method, let's say first macro, get out Copilot. And let's say that this takes 2 pieces of arguments, let's say a number as an int and a string as a string, and this returns a string. Now, all macros will be the splicing of a quoted piece of code. So we're going to do a splice of, and this is the syntax for splicing, dollar and then curly braces, much like string interpolation. This is just code interpolation, okay? And the interpolated code is going to be an expression obtained by some implementation of this macro, which is usually done in a separate method. Let's call this first macro impl. And the implementation is going to take expressions of these types and the representation of the kind of stuff that you can write in Scala is very similar to the toy example that we did for the calculators. The piece of AST is still called expr. It takes a type parameter. So I'm going to comment these out, and I'm going to have, let's call this a num AST, number AST, which is an expr int. And the expr type needs to be imported from the package scala.quoted, or simply quoted, because all the Scala packages are naturally imported in all projects. So you can say import quoted star. And this num AST takes an expr int and let's say a string AST as an expr string. And the only kind of value that you can obtain from a macro implementation is going to be an expr of something else. Let's say we have an expr string. And I'm going to leave it unimplemented for now. And this is the manipulation part. So this is manipulating the AST. And this is quoting plus reinserting the AST back as an expression. So I'm going to quote the first macro impl, and in order for me to turn this number into an expression and turn the string into an expression, I will need to quote them. So I'm going to add a single quote number and single quote string. This is the quoting part. So quoting turns these expressions into exprs that we can then manipulate in the method, and then whatever expr we obtain as a result, we inject it back into the code via splicing. So quoting and then splicing. That's the macro pattern. Okay. Now, in order for us to use a macro, we need to go into another file to be able to call this first macro, because due to how Scala is compiled, we need to have the macros separate from the usage of those macros. Now, one other thing that is important for any macro implementation is to pass a given value called quotes. So I'm going to say using quotes with a capital Q. This is a data structure that gives you access to the macros API, which also gives you the ability to create expressions at compile time, like dynamically create expressions. So let me go save this. Let me go to the usage file, and I'm going to have my, let's say, first macro usage. And this is going to be my first macro, and I'm going to import macros demo, everything so that I have access to that method. First macro with some expressions like 2 plus 3 and the string Scala. Okay, let me go save this. Unfortunately, Metals doesn't give me any information on whether this code compiles or not. Thankfully, I have an SBT terminal running behind the scenes, and this is the source of truth. And we have exception occurred while executing macro expansion because an implementation is missing. So in other words, this question mark is actually being invoked and evaluated at compile time. And this is something that's very important. All macro implementations and macro invocations are executed. So this code, this method, is invoked at compile time. So if I happen to build an expression myself, like expr with this is a simple string, this expression will be evaluated at compile time, and this expression will be assigned to my first macro usage variable. So if I happen to save these files, Metals doesn't give me any indication, but SBT does show me what's happening here. So now we have a code success. And look at this. We have first macro usage, which is a string, and we have this is a simple string. This evaluation happens at compile time before the code is even turned into bytecode. Okay, so a few lessons so far. All macros have this sort of shape, inline methods with a bunch of arguments, and the implementation is always some splicing of some expression, and that expression is usually calling a method with quoted expressions. And the macro implementation is a regular Scala method that takes a bunch of arguments. Instead of regular values, you take exprs of values, and then you can manipulate these exprs and build any sort of expr that you like. Cool. And this method happens or is executed, evaluated at compile time. Now, instead of simple expressions, let's build some more complex ones. Let's say that we want to evaluate at compile time what this int is. So if this int happens to be a constant, then we can evaluate it and you can do some checks with it. So for example, I can say val num value as num ast dot, there's a method called value or abort. If this expression is not a constant, then this will issue a compile error. Let's say val string value as string ast dot value or abort. And let's do some sort of check. For example, val new string as if num value is bigger than 3, then I'm going to say string value dot repeat num value. Okay, and maybe otherwise, I'm going to say string value dot take num value divided by 10 or something like that, divided by 2. Ignoring the potential problems of having a too short string and stuff like that, you can deal with that particular logic. And let's assume that the expr returns the macro impl is, and then you have the plus new string returned as a result. So let me go save this. And if I go back to the compiling output, we see that the first macro usage is the macro impl is Scala repeated 5 times. That's because the number AST, which is the expression 2 plus 3, is evaluatable at compile time. This is very important. And the num value is bigger than 3, so we have string value repeat, in our case, 5 times. If this expression were more complicated and unable to be evaluated at compile time, so for example, if I have a method, let's say compute meaning of life returns an int, and let's say it returns 40 plus 2, and you say compute meaning of life instead of 2 plus 3, this will trigger a compiling error. That's because this compute meaning of life expression cannot be computable at compile time in the general terms. So this expects a known value. This is why we get this compiling error. So I'm going to simply reduce that to something that is evaluatable at compile time, and simple math expressions are. So the value or abort method will trigger a compile error if this is not computable at compile time. All right, cool. Now, there are many things that you can do with expressions, many things that you can do with these ASTs. And in the macros course, the macros and metaprogramming course, I talk at length about what you can do with these exprs. This is a bit outside the scope of this video, but I want to show you some capabilities. For example, quoting and quote matching. So let me show you what I mean by this. I'm going to create a macro, so I'm going to have an inline method. Let's call this pattern matching on options. I'm going to have an option as an option int, and I'm going to mark this parameter inline so that we can see the actual expression inside this option that we're passing as argument. And I'm going to splice, and I'm going to call a PM options impl. Notice that this naming convention is pretty standard. You can see this in various libraries, in various implementations in the Scala ecosystem. And I'm going to quote the opt that I receive as argument, and I'm going to have a method PM options impl, where I'm going to have an option as an expr of option int. I'm going to have using quotes. Okay. And this is going to return, let's say, an expr string. Okay. Now, this expression contains the entire structure of the option int that we're passing as argument. So the expression itself, so for example, if I'm calling, say, option description, let me put some question marks here, or let me introduce an expr, let's say to do, so that the code doesn't crash. Okay, so option description as PM options on some option like sum2. If I pass sum2 as argument directly as it is, and the option parameter is inline, the expression itself, the constructor sum2, is being described by this expr option int. So the descriptor of the expression itself is what is being passed here. So you see here that the option description is currently to do. That's because the macro implementation returns the expr. Now, the expr itself, as I mentioned earlier, contains the description of what was used earlier in the code to build this expression. Hopefully that makes sense. And that description can be pattern matched. For example, I can say opt match. And let's say, let me run an implementation where I'm going to return a string. So let's call this result as opt match. And I'm going to have my expr result as the final value. Okay, so val result, opt match. The expression itself can be pattern matched, and I can pattern match against a quoted expression like this. So quote with curly braces is the opposite of splicing, and I can destructure a pattern match with whatever constituents this expression was built out of. So I'm going to say, for example, sum with 42. So if I'm passing the constructor sum42 explicitly as it is, this pattern match will match. So I'm going to say, got the meaning of life. In case I get a quote for sum with some sort of variable, and if you pattern match on quotes, you'll have to do the reverse of matching, which is the dollar variable. So the expression that you're going to pattern match against, this is going to be an expression, an expr, that you can then use later. So I can say got a variable. And you can also use s-interpolated strings inside code that evaluates exprs. And if you want to print this out, there is a thing called x.show. So you can print out the expression itself, and in case you get anything else, let's say got something else. Okay, so let's consider this sort of implementation. In the macros demo usage, I have option description with PM options sum2. Now the constructor sum2 is going to pattern match this second case with got a variable. And it's important to note that the constructor sum2 itself has no resemblance or has no knowledge of how this will be represented in the bytecode. So currently PM options with sum2 should match this second case. Let's check the compiling output. So we have option description, got a variable, and we have 2. If you have something along the lines of option 2, which at the runtime, say option description 2, PM option with option 2, even though at runtime these two instances are going to be the same, or at least comparably equal by the equal sign or by the equals method in the JVM, the constructor itself, the expression itself is different, so PM options will not match either one of these cases. It's going to match the last one. So let me go save these files, and you're going to see option description 2 is got something else. It's important to understand that these constructors don't really know how they will be represented in the bytecode. This code simply pattern matches whatever expression or expression description was being passed literally in the code. Okay, so this is something that the Scala macro API offers us, and pattern matching on quotes is something definitely new for most people, and I'm pretty sure that if you're watching this video, you'll probably find these as news. And in the course, I talk more about what you can pattern match and what you can extract out of these quotes. So these are super powerful, and these allow you to manipulate ASTs by just pattern matching on the respective quotes. And you can pattern match arbitrarily complex expressions. For example, I can copy something like this, like option description 3. I'm going to say PM options on options 10 dot map underscore +1. So this expression itself can also be pattern matched. Currently, it returns got something else. But if we add a case here, I can show you how that looks like. So in case we pattern match on some sort of option, I'm going to call this $O, which is an option of some type. I'm going to call this lowercase t, and quotes can also pattern match types as well before the types are erased. You can say map with some sort of other type like S. So option A, map with the type B with some sort of function. Then I'm going to say mapping an option. Let me go save that. Okay, we have mapping a function with $. $F. It's important to put the dollar signs for expressions. Okay, so look at this. We have mapping an option. And you can extract both the types, you can extract the pieces of the patterns, you can extract functions, you can invoke them dynamically, and so on and so forth. There are a lot of things that you can do with quotes. So quoting is a powerful feature. And one other thing that I wanted to show you in this video is the so-called reflection. And reflection gets a bad rap, at least in the JVM world, because reflection means inspecting things at runtime, which circumvents type safety. But in Scala, with macros, reflection also means type safety. I'm going to show you what I mean by this. So a classical case of reflection is to invoke a method dynamically by name. So you can simply mention the method name, and the runtime just finds that method by name and just invokes that. You can do something like that at compile time in a fully type-safe way by this reflection thing. So I'm going to show you a little demonstration. Let's call this call method dynamically, and I'm going to have a type parameter A on an instance of type A. And let's say we have the method name, which is a string, and we know for a fact that the method will take some sort of argument, which is an int, and this returns some sort of string, let's say. And I'm going to splice. Let's call this call method dynamically. And I'm going to have an impl on the quote instance, quote method name, and quote arg. Okay. Let's define the call method dynamically impl, which has an instance. Now we need a type parameter, a. So instance is going to be an x per a. Then we have the method name, which is an x per string. And then we have the argument, which is an x per int. We have using quotes. And this returns an x per string. Okay. Now let me start with a block. Okay. And let me show you how we can use that. So let's say we have x per to do. Okay, just to make this code compile. And in the usage, I'm going to create a simple class like a case class. So case class, say simple wrapper with an x as an int. And let's say we have a magic method, which takes another parameter, and this returns an expression like this simple wrapper called a magic with, and I'm going to returning, and I'm going to have x plus y, okay? And I'm going to have my val meaning of life and of my val result as call method dynamically on the simple wrapper 10, let's say. So this is going to be the instance. The name of the method is going to be magic method. And the argument is going to be meaning of life. Okay? So meaning of life is obviously 42, and the result is going to be the invocation of this call method dynamically. Now, the benefit of something like this is that the name of the method can be built out of simple strings or fetched from the database or things like that. The runtime reflection has its uses, but at the compile time, the reflection that I'm talking about maintains type safety, and if this method happens to not exist, then we're going to have a full compile error. So currently, this result is going to return to do because that's what the expression returns. And this call method dynamically now needs to be processed by me. Okay, now in order for me to access reflection at compile time, this quotes instance, I'm going to name it. So I'm going to have Q, which is quotes. And Q offers some methods that are in a special package called reflection, or reflect, which we have to import. So I'm going to have import QReflect. And QReflect gives us the ability to build arbitrarily complex abstract syntax trees without necessarily having the types of these expressions. And I talk more at length about the untyped abstract syntax trees in the macros and metaprogramming course, but just as a TLDR, the typed AST is x per a. The so-called untyped AST is called term. Now, the term untyped is not really proper because the term is also properly typed in the Scala type system. It's just that the term gives us less types to worry about, and it gives us more loose access to a bunch of functionalities that expr A does not. So even if this model is slightly inaccurate, at least at the beginning, it's useful to think of these concepts in this style. And in our case, to be able to access a method quote-unquote reflectively, so dynamically by the method name, we need to turn this expr into a term. So I'm going to have a val term as instance.asTerm. Now, the asTerm method is granted on an expr A if we have this import in scope. If we don't, then we don't have access to this method. And you can inspect terms with an arbitrary precision. So I can say val method is to find a method using a select term. So I can say select dot unique. So essentially, I'm grabbing a member of this expression, which happens to be the method name. So I'm going to say select unique on the term. This is the expression that I'm inspecting, and the method name dot value or abort. So this is going to be a string, and I'm returning a select object. And this select object gives us the ability to invoke that method. So the application or the invocation is going to be an apply term. So apply on this method and the list of arguments. So this is going to be list with, and we need a list of terms. So the apply gives us the arguments as a list of arbitrary terms. So I'm going to take the argument, which is an expr int, and turn that into a term as well. So I'm going to say arg.asTerm. So this is the same as me calling instance.method on the argument, but the method name is not known, at least at this point. The select.unique makes the compiler search for this method and then invoke it with an apply. By the way, the select type and the apply type are both kinds of abstract syntax trees that the compiler can then inject back. So the invocation, which is the apply term, I can turn that back into an expr string by essentially upcasting it. So I'm going to say the invocation dot, and there's a method called as expr of string. So this turns a term back to an expr string if I know for a fact that this term is an expr string. And at this level, when I'm using Scala to manipulate other Scala code, I kind of have to trust myself that the types are correctly mentioned here, because if the types are not, then we are going to get a compile error. Okay, so let me go save this. And the macros demo usage seems to also have been compiled. Let's check the compiler output. So look at this. The result is of type string, and we have a little block here. So look at this. We have instance proxy 1, which is simple wrapper.apply10, okay? And then we have instance proxy 1.magic method on the meaning of life. In other words, the compiler figured out that the result is simple wrapper 10, which is the intermediate method that you see here, instance proxy 1. So simple wrapper 10. And then calling the magic method on that. So simple wrapper 10.magic method on meaning of life. So this was figured out, so found at compile time. This is super important and super, super powerful. It maintains the strength of the Scala language and the type system without having to compromise on the flexibility of calling or invoking things by name. Obviously, if I have something that doesn't exist, like a result invalid, I'm going to say magic method 2, this thing doesn't compile. So result invalid should not compile, and we do get this sort of error. So value magic method 2 is not a member of simple wrapper. Okay, that's because the macro expansion tries to invoke the instance.method2 on the argument, and of course that method does not exist. So the code does not compile, and that is expected. So macros are extremely powerful in Scala 3. There is literally no parallel in other programming language to the kind of power and flexibility and also safety that the Scala macros offers in the same language with the same data structures and with the power of the Scala compiler. And this video only scratched the surface. If you want to learn more about this stuff, check out the Scala macros and metaprogramming course. And in the meantime, I'm waiting for you with other videos of topics about pretty much everything there is to know about Scala, functional programming, Kotlin, and everything else on Rock the JVM. Until next time, folks, this was Daniel signing off.